So let us come back after your atomic radii and ionic radii. We'll come back to the next trend of your D block element, that is your melting point and boiling point. So we'll also learn what is here atomization, concept of atomization also in this now. So as we've seen in atomic radii and ionic radii, we have a lot of variations in the graph. 3D series also there's variations or trends. We've also learned about 4D and 5D concept of lanthanide contraction. Now in melting point also, when I observe the graph, there's a lot of variation in the graph of graph shown by transition elements. So let us see the questions based on this. One important concept, whenever they're asking you about melting point or boiling point, whether it is high or low, what key point should I remember to answer those questions? First we'll discuss that and come back to these questions. Now that particular concept I'll explain in this term. Suppose if they ask you in transition metal elements, melting point first increases and shows a dip, and then in the middle, and then decreases. First it is increasing, then it is decreasing, then again it is decreasing. What is the reason? First most important thing, your answer should start like this. So in transition elements, what is the general configuration? And you have the configuration of Ns 0 to 2, N minus 1, D 1 to 10. So now what happens, as I said, the energy difference between Ns and ND, that is N minus 1D, the energy difference is very less. So both of these, they try to undergo interatomic attraction and finally form a strong metallic bonding. First most important thing. What did I say now? Let us write first. I said energy difference is very less. Okay, when it is very less, what will happen? They'll undergo strong interatomic attractions. Okay, strong interatomic attractions, then finally what does it lead into? It leads into stronger metallic bond. Okay, all these are metals, isn't it? Metallic bond. This is also fine. Now what happens when the metallic bond is stronger? Automatically I have to supply excess amount of energy or melting point to melt that particular thing, right? I have to use an amount of energy more than required because the bond formed is very strong. So hence the MP increases. This is the reason. Now next important concept which you have to remember when you answer such questions, right? So this is one concept. The second concept would be, if the number of electrons or the number of unpaired electrons are more, the melting point would be high. Remember this concept. What did I say? Number of unpaired electrons. The number of unpaired electrons are more, so MP will be more. Yes, let me give another statement. So where will I write this? Okay, I think I can erase this part of the board. Okay. So the next key point which I have to remember, this is my first key point, the second key point, third key point. Third key point in melting point is if the number of bond pairs, that means if it is completely filled, if it is stable, okay, or number of, well, otherwise we'll write if it has stable configuration, then melting point decreases. Why? You don't find the d electron participating in the reaction, isn't it? So it is completely bond 3d10 configuration or d5 configuration, you'll have low melting point. So remember that. Unpaired electrons more, high melting point. No unpaired electrons, that is it is completely stable, low melting point. So let us come back with that. So remember this concept and this concept. Now they've asked me in this form. What is the form? Why does iron have higher melting point than copper? So come back to iron. Now when I take, now this is your iron, this is here. They've asked you copper. Copper is here. This is your copper. Let us write the configuration. Fe configuration is 3d6 4s2. Now copper configuration, it is 3d10 4s1. Yes, done. Now I said number of electrons are more, higher is the melting point. So compare these two. This is how many? D is d6, isn't it? So 1 2 3 1 2 3 4 5 6. How many unpaired electrons you have? N is 4. Here in copper all are filled, isn't it? Stable configuration. 1 2 3 4 5 6 7 8 9 10. N is equal to 0 here. So the same concept I'm applying here. Number of unpaired electrons are more, melting point would be more. So this is the reason melting point of iron is more than copper. Simple. So write this number of, okay, we will not write like that. We'll write iron has N is equal to 4. Unpaired electrons. So MP is higher. Simple concept. Done. Let us come back to next question. Why do zinc, cadmium, mercury have low melting point? So where do zinc, cadmium, mercury lie? They lie at the extreme end, isn't it? After copper you have zinc, after gold you have mercury, after silver you have cadmium. So they are asking us, why do they have low melting point? Simple concept. When do I say it is low? Without configuration also you can write. You can just write zinc, cadmium and mercury have completely filled shells. Completely filled, stable configuration. When it is stable configuration, see this concept. Melting point decreases. That's it. So you have to remember this and remember this. Now let us answer this question and see. Maybe this is also similar but a bit different way of answering. And they've given me one more set. Earlier what did they give us? They've given us this comparison. Then they've given us your iron and copper comparison. Now we are concentrating more on these peaks. These peaks I did. Now I'm concentrating on these peaks. Just see. But they ask us why chromium. Okay, chromium is here. Molybdenum, right? Tungsten, right? And why are these, right? So these three elements, why do they have the maximum peaks in the melting point trends, they asked us. So why do they have highest? What did I say? Basically, whenever they're asking about the melting point, you have to concentrate only on the number of unpaired electrons. More the number of unpaired electrons, higher is the melting point. Point number one. Less the number of unpaired electrons or stable configuration, lower would be the melting point. And let us write. Now for chromium, when I have written, okay, chromium, it belongs to 3D series, your molybdenum belongs to 4D and tungsten belongs to 5D, right? So when I speak in 3D series, just observe 3D5, 4s1, 4D5, 4s1, 5D4, 6s2. And this one RE is 5D5, 6s2. So what are you observing? Why do they have highest peak in the melting point? Now, see the number of unpaired electrons, half filled. But here you have one unpaired electron. Here also half filled, one unpaired electron. Here 4 unpaired electrons, isn't it? Now see here 4, 3D, 1, 2, 3, 4 unpaired electrons here. Now when you observe here, half filled, and this is 6s2 filled completely. Now when I have to see chromium, because of the presence of unpaired electron, it is highest. And on the top of that, this is half filled, okay. But this and presence of unpaired makes the melting point of chromium higher. More than that, if I see, this is higher. More than that, tungsten, compared to these two, this is having more number of unpaired electrons, so this is a bit more higher than that. So let us come back and see. We are going to write chromium number of unpaired electron, this, yeah. And if I have to see 3D5, okay, here only I can write, isn't it? Yeah, number of unpaired electrons of 5 and 1, 6. Okay, this is stable, but I'm counting as half filled. And molybdenum, if I see 4D5, 4s1. If I have to say tungsten, 5D4, 6s2. If I have to see Re, it is 5D5, 6s2. So everywhere you have number of unpaired electrons. So you can generalize and write as number of unpaired electron increases, MP increases. That's it. Now, they've given me one more question in terms of density. They said chromium, yeah, where is chromium? Chromium is here. Where the other one, iron. Okay, now they're comparing between these two. Chromium and iron, they've given us the density. Chromium has 7.19 and iron has 7.8. So, which has higher melting point? You don't know anything about the configuration, nothing else. You want to speak in terms of density. So, we very well know density is equal to mass by volume. Now, for chromium, the this one as atomic number, double of that. So, the mass would be when I compare chromium mass and iron mass, which will have more mass, iron will have higher mass. When the mass is more, obviously the density will be more. Yes, so first concept based on density, the mass of iron, your mass of Fe is greater than mass of copper, sorry, mass of chromium. When the mass of chromium, mass of iron is more than chromium, what will happen to that melting point or this one? Let's see. Yeah, the chromium and iron, when I see, obviously the density will be higher. Okay, I spoke in terms of density. This is one concept. The next concept where I'm going to speak in terms of configurations also. In chromium, it is 3d5. In chromium, it is 3d5 4s1. When I speak about iron, you have 3d6 4s1 4s2. Yes, now if I have to compare between this and this, how many unpaired electrons do we have here? You have 1 2 3 4 5 and 6. Now see, how many unpaired electrons? 1 2 3 4. N is equal to 4. 4 unpaired electrons. Yes or no? Yes. Now when I have to see this, this is completely half filled. It is stable. Okay. Yes. Now this is completely half filled, but it is highly stable. Yeah. Now there is one valence electron existing here. So I will write N is equal to 1. When I have to compare both of these, yes, when I have to compare both of this, chromium has half filled and stable configuration, right? So both the concepts are acting on this. So it has higher MP compared to Fe. But here what is happening? You have only unpaired electron, but the stability factor also counts here. There is no stability factor counting here. So chromium is in the peak compared to iron.